Well, this is the last lecture on the advanced spectroscopic technique which we have been discussing. So, the last technique which I started discussing on is on yields, that is on electron energy loss spectroscopy, and I have discussed with you the basics of yields. Its technique relies on the aspect that electrons, when falling on the samples of any type, undergoes something known as inelastic scattering. Obviously, electrons are used for electron diffraction in the electron microscopes, and electron diffraction is mostly because of the elastic scattering, in which both the energy and the momentum are conserved. But in case of inelastic scattering, there is always some energy loss of the incident electron and the electron which has passed through, which has basically passed through the sample. This energy loss can be always due to certain kinds of electronic transitions happening in the material, or it can be actually termed as atom electron excitations which are taking place. So, therefore, if we analyze these electrons which are basically undergone inelastic scattering, we can get information regarding electronic structure, band structure, like bonding type, and quantitatively also we can measure certain amount of element present in the material. So, first and foremost thing which I have done is that I looked at different kinds of energy losses an electron can undergo and showed you that there are different types of energy losses possible. I will go back to this slide where I have shown you the first thing which happens is in a energy loss spectroscopy is division of the regions based on the energy. So, in case of low loss regions which is less than about 50 electron volts, we always have phonon excitations which is very small, actually close to 1 eV or less than 1 eV, and they are not of any significance for the measurements, because the beams which are used for measurements for electron loss spectroscopy are not so much monochromatized that we can talk about the energy split of about 0.5 electron volts. So, they are not dissolved at all. Second important things which always happens in the low loss region is called interband or intraband transitions between the electrons. As we know, the electrons moves in the orbital in the atoms. So, therefore, when an electron coming from high energy source like an electron microscope is applies its all energy to eject certain electrons from one cell, so that place becomes vacant, and this can lead to inter or intraband transitions, and this kind of things can give us a signature of the structure of the material, because electronic energies are basically proportional to the type of atoms or type of element it is, and they actually happens in the energy range of 5 to 25 electron volts. Well, these are very important, and we have already discussed about it, we will discuss more. And then you have something known as high energy loss, where energy losses are more than 50 electron volts, and things which happens there are two things. One is called plasmon excitation. You know, the plasmons are basically collective oscillations of the electrons for the metals, and where the free electrons are large, they are very strong, and there can be both type of plasmons, both surface plasmon or bulk plasmon. One is a transverse wave, other one is a longitudinal wave, because these are all collective oscillations. So, therefore, there are natures wavy in nature. And last thing which can happen is basically inner shell ionization. That means you have different cells in the atoms, K, L, M, N, O, P, we know that. So, inner cells which are K, L, M or K, L, M, basically they contains very tightly bonded electrons, and if the energy of the incoming electrons are very high, this can eject an inner cell electron, and this can lead to an ionization of the element, and that can be used to detect an element in fact, because energy levels of these electrons in the KLM cells are very well defined for different elements. So, this is actually in a nutshell the yield signals, and this is what I have discussed with you, and that is what actually obtained in yields particular signal. I will show you the yields spectra. Yes. So, the zero loss in yield spectra corresponds to elastic scattering. That means the electrons which have passed through, and you know that any kind of electron microscopist will tell you that large number of electrons pass through the sample. So therefore, this particular peak in yield spectra we have very high intensity. In fact, this is the highest intensity. This is followed by plasmons. Plasmons comes in a energy range very close to the zero loss peak, and then there are characteristics peaks like elemental peaks, followed by other things like we know as ELNES and EXELFS. They are all energy loss near edge structures or extended energy loss near finite structures, which we will discuss now. So these gives you lot of things about the electronic structure in the material. Before that, let me just go into the band structure what we started with, and where I will tell you how the bands can be. You know that yield maps can be used to get the band structure in a material. It is possible actually, and this is what has been shown in the slides. It is basically electrons which are ejected from the core levels, like K, L, M, N, just now I discussed, by the incident electron can scatter only into available states which are available to them, and thus the energy imparted by the incident electrons to get them basically to these transitions will reflect the density of states. It's as simple as that. So ionization results in electrons which are ejected from the core states into the empty states above the Fermi levels, and when that happens we can get informations of the band structure. This is why these are actually called edges, not peaks, because they are just onset of transitions. They are not actually talking about the whole transition, they are talking about onset transition. Let me explain. Let us suppose this is what the first picture here shows. This is the empty state, then this is the Fermi level, because below Fermi level all the states are occupied, above Fermi level states are not occupied, unoccupied, and below Fermi level you have conduction and the valence bands, as you can see here. Well, now let us assume that K, L, M, there are 3 cells which are inner cells, and energy levels coming out are basically suppose electrons which are ejected from K cell or M cell or L cell can basically have energies sufficient enough to travel into this conduction or valence state. In fact, it may have energy sufficient enough to cross this, many cases cross this Fermi barrier or Fermi level and enter into empty states. This is highly possible. Here I am just showing you a case of nickel oxide yield spectrum, where you can see even the M cell energies which are electrons which have actually moved inside the conduction valence band very close to the yields very close to the Fermi energy level as led into a peak formation here, and so this is the M transition, and this peak is correspond to those kind of states which were unfilled actually at the beginning in case of NIO yield spectrum. So that is how actually the band structure of the whole material can be obtained. This is what again showed here. This is a plot between Ne versus E, as you can see here, and this is the Fermi level. So these are the filled state and these are the empty states, and then you have basically density of states can be shown like this. So if I do certain kind of experiment like that, that means if I have electron energies more than the transition energies, okay, then it can eject the electrons from the cells with sufficient high energy so that these electrons can move into these empty states. You can get something like this kind of extended structure, fine structure information in the yield spectrum. Well, that is very dependent upon what kind of transitions you are allowing. Like in EDX, observable edges are directly related to the elemental cells. That means we can always see K, L, M edges in EDS, we know that, but depending on the atomic of the material also we see that. But here you can have even intraband transitions, like within the M cells you have M1, M2 through 3, M4, or within N cell N1, N2, 3, N4, N6, 7 like that. So these transitions are also possible. These are actually spin orbital transitions. Now obviously it can also give us information about the energy loss nearest structures which are there, which I have shown you in the last slides. So let us now talk about in terms of schematic pictures. This is the energy band. You see, this is EV versus distance plot on the left side, and then you see this is the Fermi level, this is the valence band EV, and these are actually different atoms 1, 2, 3, 4, 5, and this within one atoms, these electrons are sitting in K, L, M, N, O, P, but these are the 3 unit cells which are shown inside or inner cells, and this is the conduction band. So, up to these field cells are there up to actually a Fermi level, and they have empty states, and above empty states you have valence band. So, actually in ELS what happens, you can have an incident electron with a sufficiently high energy, it can eject one of the electrons M, L, K in the cells, and they can then move into these empty states, and if they have even higher energy they can even move into the valence bands also. Now if I go back to the right hand side structure, it will be more clear. So these see K, L, M are the core states, and they have valence bands, and above that you have conduction bands, and then EV is there. So these kind of transitions from L2, 3 to even empty states can give us information regarding this part of the energy levels. And these are all actually called electron loss energy, electron loss nearest structures, or extended electron loss finite structures. So first one is gives you the DOS, or density of states in the conduction bands. These are actually very well known and well understood now, and they are used extensively. Second one, it's not so widely used. It actually can give us information regarding chemical bonding, but it is still a lot of research needs to be done to understand these electronic transitions for electron extended energy loss fine scale structure. This is just like XAPS in case of X-rays. Let me give you some more things about ELNS, how it can be used as a fingerprinting. In fact, this is what is actually people do nowadays to know exactly the electronic states of a particular atom. First, let us talk about titanium. Titanium in 3 different compounds: calcium titanate, titanium dioxide, and Ti2O3. So in both calcium titanate and TiO2, the titanium actually has a +4 states, and in case of Ti2O3 it has +3 states. If I look at the ELNS spectra of titanium in all these 3 compounds, I could see that depending on this electronic state, there is distinct difference in terms of this ELNS spectrum. In case of calcium titanate and titanium dioxide, you can see 4 splits, but in case of Ti2O3 there is only 2. Not only that, there is a shift of energy losses to the lower values for Ti2O3. So that means L23's edge obtained from Ti2O3 differs markedly from the tetravalent compounds like TiO2 or calcium titanate. Not only that, in fact, one can look at differences of TiO2, titanium state of titanium in TiO2 from a grain and from a twist boundary. It can be done in electron microscope. You can see a boundary of the twist type or tilt type. You can see the nature of the spectrum actually remains same for both, whether titanium dioxide is present in the grain, inside the grain, or at the twist boundary. But there is a distinct difference as far as the energy levels are concerned, they are not same. So there is this little difference. So therefore Ti-L23 edge from the twist boundary although closely matches with the edge structure of TiO2 standards, but the fine structures are different. That cannot be discussed within the framework of this lecture, because one needs to know what is tilt boundary structure and what all things can be there, a twist boundary structure. So therefore it can be done. This particular things are taken from Seth Taylor of GE Global Research, and they are very important information. Well, so after giving you band structure, ELNS, or the energy loss nearest structures, let us just compare EDS with yields. There are many comparisons for EDS and yields. I will give you a chart also at the end of this lecture. Yields are actually much more, quantitatively, qualitatively much more superior than ADS. That is what you will be taught by different books. As you have seen, number of counts in yields are very, very large as compared to EDS, first of all. And both of them function actually like a collection angle. EDX collects small angular distribution of the all emitted X-rays, but yields actually inelastic scattering of electrons are largely forward scattered, so therefore they are collected, and that is why if the signals are more, so therefore there will be higher quality of data. Now it can be shown here also. You have a thin specimen here, electrons are falling from the incident beam, and then X-rays generated by detector by the EDS detector or X-ray detectors normally contains this basically within a small window. You can see this is the window, normally contains -4 to -2 of the emitted X-rays. That means we collect very small amount of information which is generated. That is the problem in EDS, in TM. That is why actually nowadays, because of this problem, many microscope, especially the high end microscope, uses several EDS detectors, at least 4 within the TM column, so that the quantitative information, the quantity of the X-rays which can be gathered from the samples could be very large, or at least it can be increased. In case of yields, the electrons pass through a sample and we collect the solid electrons which are undergone inelastic scattering in a solid angle of pi beta square, or beta is incident angle, or this actually this angle, it contains most of the energy loss electrons. So that is why yields is always preferred, but yields requires a lot of alignment of the microscope and many other things, and it is costly compared to EDS. That is why very few labs has EDS. Now more on yieldness if we want to give it, but I do not want to talk much details. This is basically, as I said, they are all fine scale structures and they can be used for determination of the fine scale structure. Yieldness comes very near lower energy levels than the EXE LFS, and ELXE they all talk about density of state. In fact, you can obtain a radial distribution functions also, because it talks about the near element configurations of a particular atom, and therefore it is possible to obtain the radial distribution functions. So to give you some more ideas about that, there are two things, one is important which one is to consider. One is called single scattering and another is called polar scattering. When you have atoms in a surrounded by several atoms, suppose this black atom is surrounded by 6 atoms, other atoms types, and this is what actually we would like to know, how these atoms are distributed around the black atom. So in a polar scattering, the electron which comes like that, it can come from the actually get scattered from the black atom, then goes and get scattered from all the 6 atoms and then come out. That will carry the information regarding all the surrounding atoms, and that is what actually they are in electron loss near edge structures. But on the other hand, in case of extended electron energy fine scale structures, you have only single scattering. So once electron actually scattered from the black atom goes to the one of these surrounding atoms and then comes back. So this is just for sake of understanding or convenience I am talking about. This is all available in these books which I already referred to you. So this kind of scattering actually are reflected in the X. That is why in XCE LFS you have only very small minima present, but in case of ELNES you have large variation of the minima or maxima. So these signals are not so strong, but these signals are quite strong and fine, can be used to determine density of states of band structures. But bonding type information which are there in the XCE LFS is not so clear, it is still under investigations, or this has to be done. Well, after giving a lot of things about the different kinds of information which yields can generate, we need to talk about what is the kind of resolution we can get, or what is the kind of spatial resolution rather we can get. Nowadays costly microscopes come up with a very nice beam, fine probe, stable beam, but still for the best performance you need to have a very thin specimen, because the more thicker is the specimen, there will be more chance of inelastic scattering, and that can mask the information which are coming out from the electrons which are inelastic scattered through the sample. We also need to have electron gun of fake type, that is the field emission gun, because field emission guns gives you very high brightness of the beam and coherent, because energy spread of the electrons in the field emission gun is very small. So therefore, and also because high brightness, so you can always have a small probe, and normally the fake has a probe size less than nowadays possible, about 2 angstrom. So we can actually obtain resolutions of that level. This is what has been shown. Suppose you have a beam which is focused on the sample of diameter t, and then once this is passed through the sample, you can see the spread increases. So therefore, resolution actually not only depend on this size but also this size. So that is why we need to have a finer probe. So this size is finer, this will be also finer. That is what I am saying. And in case of thermodynamic emission like tungsten or the lab 6 filaments, the probe size is orders of magnitude larger. So therefore, you cannot get kind of information which you like to get from the microscope when you are analyzing the samples. Second important which you also like to know when you are doing such a kind of investigation is the sensitivity of the yields as opposed to EDS. Sensitivity means if I have an element present in suppose 0.01 percentage, can I detect? All well said and done, EDS cannot detect an elements, or rather resolution of EDX actually, they say sensitivity of EDX is very poor when the element percentage is as low as 0.01 percentage. So the minimum detectable mass in case of EDS is tens to hundreds of atoms, but with yields it will be very large, it will be hundreds of atoms. So that is why the yields actually is better, and so it depends obviously on the microscope and sample. This is what has been shown here, minimum mass function detectable weight percentage versus spatial resolution. You can see here this is the nickel and Fe in 100 kilovolt analytical microscope, this is nickel and Ab in 30 kilovolt analytical microscope, a very large probe size, but you have a detectability is very small. That means you can detect 0.01 percentage of the mass, but here you can detect only 1 percentage. So in case of copper, manganese and copper actually for 120 kilovolt AEM analytic electron microscope, this is what is the case, but in case of FEG, basically you can have very small probe size, and you can also have minimum mass fraction as low as less than 0.1. So that is why we use always FEGs. FEG means the field emission gun electron microscopes. The last thing which I am going to talk about is energy filter imaging, or what is known as EFTM. As you know, the electrons which are coming out from the sample, which are inelastically scattered, they contains all the chemical informations I showed you. The type of element presence, the what's called amount of element present, we can also do that, the electronic states. So why can't you use these electrons to map actual image? So that is known as energy filter imaging. Obviously, if one needs to map properly, you need to filter the electrons which are inelastically scattered depending on the energy levels. So I will tell you how it is possible as the slides are shown. So what is done here? This is a simple map of an yield spectra. So there basically this is what the sample is sitting there, this is a beam screen, and the energy inelastic scattered electron passes through aperture, then some alignment coils, then the magnetic prism, then it passes to 6 quadrupoles and 6 sextupoles fall. Finally we detect them in a CCD detector. So we can actually map these electrons on the image, that is what I am trying to say, and that can be done as I said by energy filter. So what can be done actually here, the change of my configuration in a microscope. As you see, this is the specimen, this is the objective lens, and there are all intermediate lens, and then once these things are coming out from the intermediate lens, it passes through this kind of setup which is known as sectopole lens gamma filter. is patented by Gatton Incorporation USA, and they can split actually the inner scattering electrons in different energy levels. They can filter actually, and then it can passes to set of other lenses, and then we can get the image. So that means you have need to attach this part inside the column of the electron microscope to obtain this kind of energy filter imaging. That is what I am to say. So that means extra cost. Basically you have to add these filters within the columns to get energy filter imaging. Let us see how this is basically done. It is nothing but a contrast enhancement technique, as I said. It improves the contrast in the images, also diffraction patterns, by removing the inner scattered electrons that produce the heavy background. That is the first thing. It is also a mapping technique. So first thing is we can do is that we can remove the inner scattering unit, you can block them, all of them. We can only have image produced by elastic scatter electrons. So that way the quality of the image or contrast of the image will be improved. That is the first thing one can do. Second thing one can do is use the mapping. EDS is used as a mapping technique. So this also can be used to create elemental maps by forming images with inertia scattering electron or particle energy levels. Also this is an analytical technique. It can record your electron energy loss spectra or even maps to provide precise chemical analysis of the samples. So that is actually in a nutshell an EFTM can do. So first thing I will show you probably the first example, and this is I think no need to show you. This is actually exactly what is done. I have shown already to you. So let me skip. And in a energy electron magnetic spec prism is needed to separate the relative wavelengths. That is what is done here. You see this is the energy loss. This is what is called scatter, inertia scatter, elastic scatter. So therefore you can separate them, and therefore if I put a filter, if I allow only this beam which is elastic scatter, and then I can basically get nice images, contrast enhancing. If I only these ones elastic scatter electrons, then I can get much other informations. That is what I am trying to say. So you can use a prism, electromagnetic prism here extra, which is nothing but a omega filter, and to separate them out. In fact, one can actually take this inertia scatter electrons and then separate them out depending on energy levels. That is also possible. So let me give you some examples. This is taken from Rudolf Gitman from Max Planck Institute Biochemy, and as you see here, this is basically a zero loss contrast enhancement by zero loss filtering, and you see here once this is the original image, this is after the filtering. So you can see there is a huge change from the contrast. I do not know whether it can be seen on the screen, but at least from the image I can see this lot of other features have vanished, and you can see even the corresponding diffraction pattern quality has improved. So you can always claim that using EFTM we can always create better images and diffraction patterns. To give some more information how energy filter TM can be used to produce better diffraction patterns, this is the conventional TM. We can see sticks passing through this, and once you map the intensity you can see this kind of broad things, and also followed by these small peaks. But once you use energy filter TM we can enhance these small peaks. So what you see here very clearly changing with electron diffraction pattern, these brighter spots are surrounded by 6 weaker spots which is not visible there. So that is how actually you can improve the contrast of the electron diffraction pattern, which is not possible use other. So here we have removed all the inner scatter electron by using the prism. Well, one can actually create an image using these electrons that are slowed down by the interaction of the specific elements, and they are all called electron spectroscopy. That is what I showed here. So basically it is a inelastically scattered electrons which are produced image, and this is accomplished by increasing the accelerating voltage of TM precisely by the additional energy needed. One can go actually up to 100,000 eV. What is done here is simple like this. This is the global imaging setup. So this is what is the quadrupole gamma filter, omega filter. So you have a specimen, electron energy comes, energy loss, and then it passes through that, and then you can basically have elastic scatter electron is basically without slit. So if you use a slit you can separate them out nicely. This is what is actually done in omega filters, and one can use different kinds of filters. There is no need of showing that. The Gaton has different filters, DO also have filters, different components are making different filters. Last things which I am going to show you is called stem yields. Stem yields in the sense that it can be used to determine the particular atom present in a high resolution or microscopy actually. What is done is, let me tell you that. So suppose this is the atomic arrangement of certain certain compound or elements, or let us say compound here because there are different colors atoms. So you have an electron falling onto that, and then each atom has different scattering power, right. That depends on the atomic electronic configurations. So depending on the scattering power, electrons they will get scattered at different angles. Now if we apply an annular detector like this is annular, there is a central hole, it is like this central hole, and this is the detector. So if I have annular detector, I can collect the electrons coming, scattered electrons coming at different angles from the incident beam, this or this or this, like that, which is scattered after it passes to the sample. The sample is here, and once I correct that, and I know that different atoms have different scattering power, so therefore I can actually image the atoms in high resolution microscope. At the same time, if I take yields from each of these atoms atomically, I can detect what atom is present. So therefore by using together STM and yields, one can actually determine the atoms in the high resolution electron microscope, which is not possible so far. But with the advent of new kind of contrast imaging like in Titan, this has become obsolete, because in Titan you can get contrast from even each atom differently. You do not need to actually do the stem. So I will give you some example of EFTM. This is just different layers in a thin multi-layer and thin film. So you can see the contrast here is different than the contrast here. So you can actually see this is graded silicon germanium multi-layers, not SI layer between them. There are only two monolayers. Single molar detection is very easy. So you can see single molar. These are high resolution images. You can see even the atomic planes, and rapid acquisition also possible. So you can quantify that. This is again taken from our own work. This is basically I have shown you at the beginning of this course. When you deposit copper using pulse electrodeposition techniques, we always use thiourea, and thiourea has many roles to play. It can control the nucleation mechanism for doing thin film deposition. It can control the growth also. It is postulated that thiourea contains a lot of sulfur, and sulfur gets collected at the grain boundaries of the grains. This is a grain, copper grain nanocrystalline, you can say approximately about 40 to 50 nanometers, and once they are collected around the grain, that it will be present in the grain boundaries, and these sulfur atoms then can pin the grain boundaries for further growth. So therefore thiourea can act as a gain inhibitor, gain growth inhibitor, and that can be probed using energy filter imaging. So if I use sulfur energy edge, that means if I only allow the energy loss due to sulfur atoms in the yield spectra, and then I will image that onto the image. So I can see that all these gain boundaries are getting brighten up. You can see here, you can see there, so you can see there. So that means indeed sulfur atoms are present at the gain boundaries. So that means our postulation that thiourea act as a gain growth inhibitor can be proved by this way. This is now published, and this is now published in the reputed journal. So one can actually look at details, but it is possible to take up certain kind of issue and then do the energy filter imaging and to show that these are actually true. Well, one can also actually do much better things. This is again taken from my own work or our own examples. These are actually nanoparticles created when you leach aluminum, nickel, cobalt quasicrystals. So they create this kind of blocky crystals, and you can see they are actually nickel cobalt FCC, and nickel cobalt has almost atomic numbers very nearby. So it is very difficult to say that nickel or cobalt present in these particles by EDX analysis. So, only here we can show is by using EFTM mapping. So, you can see here this is a big size particles, even more than 100 nanometers, quite close to about 250 nanometers. You can map nickel and cobalt in this, and if you look at carefully, the nickel is much less in these particles than cobalt, because cobalt map shows much brighter regions than the nickel map. And if I do it using a function of size, suppose if you go to intermediate size, you can see still nickel quantity is less than the cobalt in those particles. If you do the nickel and cobalt map, these are impossible in EDX actually, you cannot do that because their nickel and cobalt's atomic numbers are nearby. If you go to very small particles, you can see, suppose look at this one, nickel and cobalt distribution is almost uniform. You may ask me, what is the need of doing this? Well, as you know, these small particles which are actually alloys of nickel and cobalt nanoparticle, they are used as a catalyst. So, catalytic behavior of those particles will depend upon the elemental distribution and also the atomic electronic structure. So, by using yields, one can actually obtain all kinds of informations and then use it to understand the catalytic behavior of this. This is what is our aim also to do that, but I am showing a part of the work. So, by this way, we can actually go down to very small particles, which is actually approximately about 40 nanometers, and do mapping nickel and cobalt. This is not so good, but still you can see cobalt is almost as quantity is almost same as of nickel. So, by this way we can actually do all kinds of analysis. So, as I said sometime in the lecture that I will tell you detailed comparison of the yields and EDS. Well, yields has higher spatial resolution as EDX, EDX may be affected by background scattering. Yields has a higher energy resolution than EDX, around 1 electron volts. Yields is better in detecting lighter elements than EDS. EDS can be used to detect elements which are atomic number less than carbon or C6. Yields contains information of electronic structure which EDS does not contain. EDS is easy to operate, that is why everybody uses and quick for qualitative analysis. However, yield spectra from thick specimens may be difficult to intermediate because of the poor scattering which I have shown you. Interpretation of fine structure sometimes requires software, lot of sophisticated calculations which I could not show you because of the time constant. So, with this I conclude this lecture. The next lecture I am going to start with the surface characterization techniques, mostly XPS and the OGR spectroscopy, and move on.